So welcome to our DHI webinar. Today I have the pleasure to offer this special webinar associated to groundwater modeling within the mining context using FEFLOW. My name is Carlos Rivera. I'm from DHI Germany, based in Berlin. From my background, I am a civil engineer, PhD in hydrology. I work in DHI since almost 7 years, and within my areas of expertise. And I work a lot in unsaturated flow modeling, automatic calibration, reactive transport, and of course, the topic of the webinar today, mining and the context of groundwater in mining applications. So what is actually coming in this webinar today is I will give you an overview of the different software features that it will make your life easier to work in the mining context and groundwater. I will present a couple of examples within DHI. As you know, due to confidentiality, I will present mainly the concept of these examples, no? And at the very end of the webinar, we will give you a live demonstrations, how to build quickly a FEFLOW model for mining applications. So we have different solutions for mine water management, from designs, operations, and closures. From design, so basically you can use our technology, DHI, FEFLOW, MyG, and other softwares for mine dewatering, mine flooding, river and stream diversion. So this will be mainly surface water modeling. In terms of operation, DHI offers a very strong platform to link all the different models, so groundwater models or catchment hydrological models like MyG with our mic operations softwares, where you can real-time monitor information, generate a scenario analysis, and try to actually understand and provide a forecast of different processes happening in the mine. Closure, mine rehabilitation, hydrology, acid mine drainage, etc. These are processes that we can easily model. I will show you in the presentation a few examples about reactive transport, so where we will touch the topic of acid mine drainage with FEFLOW. So I saw many of you are already all users of the software now, but I see also new names, so it's worth it to actually say a few words about the software now. So FEFLOW is a simulator for all common processes of groundwater modeling. This basically means flow, mass transport, heat transport, and a combination that you can imagine in between all these different classes. Everything happens in one single user interface. The user interface is a productive interface, so it's really targeted to industrial users. The history of the software is really old, so we are doing this since the 79s. This was the first release of the software, and then in the 90s we have the major commercial product that was the FEFLOW Classic, so the version 5, and then DHI continue redesigning and improving the software until today in 2012. We make a very big improvement of the software by bringing the the Qt interface for the graphics now. In 2015, with the FEFLOW 7 version, we also discovered the topics of unstructured mesh in 3D and open really many doors for groundwater modeling and mining applications. FEFLOW in the mining context is used for different application cases. So we have mine dewatering typically. So you introduce your structure of the mine, different pit levels, pit shells, and geometry in FEFLOW. And using the different budget methods, you will be able to estimate the volumes that you require for the dewatering, and also predict what is the uncertainty of these dewatering volumes, with combination of our DHI tool for automatic calibration uncertainty analysis, FEPAS. We can handle problems of slope stability, so FEFLOW, based on the pressure distributions, can give you easily distribution of pressures in a cross-section or in a profile, which can be then supplied to your technical professional. Mine closure, so all the processes relevant to mine closure, rebounds, peak lake, and everything can be handled in FEFLOW. We have a couple of examples during the webinar. Regional impact assessments, so all these mining applications happen in a regional context, so we are interested to know what is happening actually with the environment. So you can use the software as a modeling tool to investigate possible regional impacts, drawdowns, water quality impacts, etc. Acid mine drainage, water, surface water interaction. We have a couple of options where you can use to model surface water and groundwater interaction. So either you simulate this from FEFLOW by prescribing the information directly to a boundary condition, or we have developed through the time different specialized solutions. I will talk about the so-called IFN lakes, able to simulate lakes and interaction with groundwater, but we also have technology more sophisticated where you basically solve hydrodynamically the surface water calculations and provide this information to the software FEFLOW. Pit mines, geometry, underground mines as well, so we can easily integrate the geometry of underground mines, simulate the advance of these different voids or excavations dynamically, so transiently in the model, tailing facilities, etc. Relevant methods, so we have Badelson and pore pressure distribution. So the processes that we are solving are happening in the interface unsaturated zone and saturated zone. So we need to have a strong solver to handle these processes. We have cases of density-dependent modeling, especially in Australia. And also, I will explain later the example of Fortescue Marsh, where we have a hypersaline systems combined or used simulated in FEFLOW. You require to have access to advanced tools of programming interfaces, so the software can do many things, but obviously there are always new ideas, new concepts. All of us are innovative, so we have the flexibility to combine all our different APIs, actually modify the software as we want. No? So we can extend physical process of the software, or we can also establish different technologies. So in this example, we have the recycle of groundwater flow, so pumping in one location and reinjecting in another location. This can be easily done with a programming interface in FEFLOW. We have cases with size and complexity. Is a multi-scale problem, so we have open pits, open cast mines, embedded in a regional context, so we have to deal with local processes, so we have high velocities happening, no infiltration fronts in the area of the pit shells or walls, but all of this is inside a big regional model. We require complex meshes, so we have unstructured grids which can accommodate very good to all the different geometries from the regional settings. We have integration to geological models. We have tools for calibration, scenario, and uncertainty analysis. We have a PES integration. We offer a very nice parallelization scheme with no license restrictions. So if you have a professional license of FEFLOW, you are technically allowed to run as many simulations as you want. So it really depends on your hardware capabilities in the company. Just mention a few of the examples that actually are involved in this mining application. So the most common is CPES estimation. So we want to estimate, okay, what is the dewatering volume that we need to pump up from the system? So here comes the question, okay, I can bring this in a model. I have one picture, but I can also extend this situation and define what is my worst case scenario. So what is, maybe comes a flooding event, so I have higher rises of groundwater levels. So I would actually like to be in the position as a modeler to understand all these worst case scenario cases. So FEFLOW can give you these options, not in combination with our automatic calibration tool FEPS. Regional impacts, we can estimate water table drawdowns, possible release of the distribution of contaminants. So as I say, FEFLOW can solve mass transport, conservative or reactive, and a combination of all of these. We can work, or we can provide information relevant for your technical applications, so like slope stability, what is the location of the water level, pressure distribution, etc. Last but not least, rebound and reclamation forecasts as well. What are the challenges in all these tasks is multi-scale, so we have local, very specific changes of the flow field in a regional model, transient mechanism, so it's excavation happening over time, so we need to have a software that is able to account all these different geometrical changes in one single model. We have also the position over time, if we are talking about tailing facilities, and we need to understand, okay, how these geometrical processes affect our dewatering or rebound. Complex geometries, it never happens that a mining model is embedded in a simple geology or hydrogeological setting, so we have to be in the position to solve and to approximate as much as possible to the reality with our meshing technology, so we can generate faults, fractures, embed these systems easily in the model. We are talking about technical structures like mine pits, tailing, waste dams. So everything has to be in the model. We can introduce this with the structural meshes. And of course, we need to have integration of technical processes like drainage or dewatering. Difficult is processes. So we could be solving simply flow, unsaturated flow, variable saturated flow by solving Richard's equation, but maybe we have a situation like in the Western Australia where we have high density systems, so then we need to couple flow and mass transport with the software, We will be interested to estimate water quality, so we need to have some capabilities of geochemical modeling, so we can do a lot with people, but we can also interact with other softwares, We have processes of surface water and groundwater interactions, and of course we need to calibrate to scenario analysis, sensitivity analysis, and uncertainty analysis with the model. So in few words, what is the graphical interface of the software? So our philosophy, the DHI philosophy is to have one single interface. So we offer you one single interface where you can do basically the model setup, simulation, evaluation of the results. So you don't need to handle a lot of files. So you have one single file, the FEM file, .fem or the result file .dat file. And you just need these two files to operate with them, with the different models and maintain the data. So you have in the interface very innovative panels and tools where you can track your different time steps or results of the simulation. We have a very flexible licensing levels and different options. We can do from very simple box models to really very complex regional models with amazing geological or hydrogeological settings, and everything is one single interface and one single package. We put a lot of effort in visualization, so very easily you can create cross sections, profiles, based on polylines that you manually build or just import. You can display 3D, 2D maps, create videos, etc., export all this information in high quality images, videos. We know that this is a nice to have, but it's also very important to actually have all these methods, because all of us are always in discussion with technical professionals, but also with public authorities, communities, etc. So we need tools to present our results in the most easier manner. Few examples of visualization. We extend a lot the interface for importing, exporting, so we can work with different GIS formats, so shed files, CAD, DXF, geological software, so we have interface into Leapfrog, GoCAD, GeoModeler 3D, etc. Let's move more into the details. So let's talk about flexible meshes. So as I say, FEFLOW can do a lot of things with the mesh, and I try to actually here in these few slides just give you some ideas what is possible to do with the software, what we have been always doing since the 70s and what is now possible with the new and structured meshes. So you see on the left side, you will always have the classical representation in FEFLOW. Classical means we preserve the continuity of the layers. In this example, we have a fracture, and on the right side, you have the setup that it will be possible to do with the structural meshes. So clearly you see certain advantages, so you don't have to maintain these minimum thickness elements. Sometimes depending on the geometry that you are passing into the model, no, these elements could be very elongated, so you can also minimize the number of elements, and this will accelerate your calculations. No? If you talk about geological system, let's say this is a clay lens. Here we can represent very easily with layer continuities methods, you know, like on the left side, or just pinch out the layer in the location so we don't need it anymore, like on the right image. We want to simulate or to include as much as possible details of our excavation, no? So we can handle all this with FEFLOW, with the classical layer approach, where we basically represent the different pit levels and follow the geometry of the levels with the elevation of the slices of layers in FEFLOW. No, you can also do this with an structure method. So we did 2 years ago a very big project in South America, where we basically simulate 36 years of mining plans, including each individual year of the mines in the FEFLOW model, and this with an structure meshes. So we have a change in geometry, no problem. You can activate or deactivate the elements. So for those working with ModFlow, this is a little bit different, the concept here. So we don't do a deactivation to solve the unsaturated flow. We basically deactivate the elements because we want to represent changes of the geometry, excavation, advance of mining plans, advance of tunneling, etc. And nicely, you can change properties of boundary conditions in parallel with these geometrical changes. This is an overview of the different processes or the different workflows that you have to generate a mesh in FEFLOW. So basically, you have different paths that you can take. So you can start in 2D, you generate a mesh in 2D, and then you can extrude the mesh in 3D, adjust the elevation, and then you finish with your 3D layer model. Maybe your geology is very complex, or you want to do some specific modifications to the file, so then you need to basically extend this 3D layer model to a partial end structure or to pinch out some layers. If you are in the position that you have a very good geological model, so you work with any of our acceptable formats, and then we can read your geological data and build a 3D super mesh. And with a couple of clicks, you automatically build a 3D structure mesh in FEFLOW. So what do you, where do you actually use all these different methods? So we have different strategies and different workflows depending on the type of data. Quality of the data is also very important, no? And you will decide these workflows or this path in the methodology depending on this. So if it's possible, you can work always with layer prismatic elements, so because they're easy to handle. We work basically in 3D, but all the views are in 2D. If you need it, if you want to have some artificial underground or some inclined faults, wells, etc., you can also take a part of the model and actually remesh this part of the model and include these special geometries. No? If you have some pinching of layers and upcropping, you can also resolve these problems by local remeshing. If you have a complete and clean structural information coming from a geological software, you can import this information and generate a mesh in FEFLOW. This is the example of the geological software. So here is, we make the bridge between geological information and groundwater modeling. The motivation behind is because we put a lot of effort building this model on the left side, no? And on the past, we have to simplify all this effort to actually put it in FEFLOW, because we have to maintain the layers. We need to have certain level of reduction because the number of elements were large, etc. So now it's relatively easy. So we try to acknowledge the existing information from the geological software. So if you have some faults or your different geological volumes are prescribed or are separated by surfaces, so the mesh generator will take this information and build up a model from this point. This is an example using GeoModeler 3D. Intrepid Geophysics in Australia as well. You have here a structure mesh. This is the geological model. this is the mesh in FEFLOW, and this you have here the full structure mesh. Complex physical processes. We need to solve Richard's equation because we are handling variable saturated flow. Few examples of application are underground constructions like underground mines, tunnels, pipes, artificial recharge is also very important. We have this recharge, this infiltration or wet front has to travel the unsaturated zone, so we basically need to have a proper estimation of the velocities generated by these different gradients from the artificial recharge. Stormwater infiltration, we have seepage through dams, so you will like to understand what are the seepage fluxes through different infrastructures, no? But we also have other cases where we have design of industrial porous media, really small scales here. Fractures, so all of us has to always deal with fractures and networks, so we have multiple approaches to simulate this. So now I'm bringing only one single approach, is the so-called discrete feature elements approach. No, basically you have an element which is either 1D or 2D, which enhance the conductivity of the system. So you have a pipe here with increase of conductivity, you prescribe the properties, cross-sectional area, hydraulic radius, and FEFLOW estimate effective conductivity, which is superimposed to the conductivity of these elements. Like this, you simulate preferential flow patterns through fractures. Happens that we need to isolate these fractures, so let's worst case or the extreme case will be a second porosity system now. So we brought in the last version of the software the approach of dual node connector, where basically you separate your fracture from the matrix that you're solving, no? And this separation is done by a 1D connector. So you create a second imaginary set of nodes. These are called dual nodes, and we solve in between these connectors a 1D problem, so a Darcy problem, and we can migrate fluid, mass, or heat between the fracture and the matrix with this approach. We can represent faults as a barrier, no? You can disconnect the fault or the fracture from the system by using this dual node approach. Meaning, so you have two parameters. You have a so-called coupling length and a modulation function. So this coupling length, basically, it will control how is the transfer. So if your length is relatively large, that the flow between the matrix and the fracture will be retarded, no? Like this, you can simulate this possible flow barrier in the system. You can use these approaches to simulate drainages so horizontal drainages or inclined drainages in the pit walls, no? So we have here a very simple example, a discrete feature. So when the element is combined with the boundary conditions, and in FEFLOW you have a nice possibility to define how do you want to actually change the effective conductivity of this pipe, of this drainage due to or in partially saturated or in dry conditions. So you can choose what is the best for you. Water quality. So we have multiple methods to understand the contaminant transport now. So few of the key issues that we are all interested in are risk analysis. So we want to know when is actually coming this contamination from. So what is the time, the arrival time of this plume? What remediation techniques we can use? So do we need to pump? Can we use natural attenuation methods, or they are not applicable? We have a possibility to solve reactive transport in FEFLOW or use other software like FreakC. We can do reactive decay, cases of uranium mines, for example, or other radionuclides can be easily simulated in FEFLOW. Saltwater density-dependent flow. Again, example in Australia, I will show you just in a minute now. Cases of coastal saltwater intrusion. saltwater upcoming of wells, contamination and remediation. You have aquifers of freshwater storage in saline aquifers. DHI has multiple projects in Doha where we try to actually store freshwater in deep aquifers now for later water supply purposes. We have a connection to the very famous Freak Sea from the United States Geological Survey, USGS, where we can actually couple FEFLOW for solving flow, mass, heat, and heat transport with the complex geochemical transport Freak Sea. So these two softwares are talking all the time. Freak Sea is feeding data to FEFLOW during the calculation time. What you can do is mineral dissolution, precipitation, sulfur reactions. No, you can include gas phase exchange reaction, so you can solve the gas phase in FEFLOW. So you can, for example, provide what is the partial pressure of CO2, and then use this information to solve the biochemical processes. If you have temperature and pressure dependence reaction, you can use it in FEFLOW. So FEFLOW solve heat transport, can send information of temperature to Freak Sea, and the reactions can be on demand updated. No? And we can do complex kinetic reactions with FEFLOW, and also from the side of Freak Sea using the batch calculation from the software. So here is, I try to always make a link of these processes to some examples that we have in DHI, but due to time limitations, so I just will present two examples. No? So one I think is very interesting for you because you are based in Australia now, so we want to make this connection with the local conditions. So it's a project that we developed already some years ago, but it's still very interesting. It's very interesting because it's actually challenging. It's a challenging calculation. So we try to tackle the case of mine dewatering with the FEFLOW model. We solve flow, mass transport, and there is recirculation of the flow. Just to give you a little bit of content, so we have the Fortescue March, and we simulate basically this so-called crowd-bricked mine here. No, from the hydrogeological situation, this is a typical cross-sections. No, very interesting to see is the lower section of the PowerPoint slide. So we have fresh brackish water lens. No, there is a groundwater system that is dominated by hypersaline. So all this, it's a really important processes that we can not avoid because flow will be dominated. So flow will be dominated by density gradients here. And we need to incorporate this process in the system. So here we have our conceptual model. We have one of the pits. Now we have a so-called managed aquifer recharge system, the MAR schemes, where we basically reinfiltrate some of this water back to the aquifer. No, main problem is that this reinjection is saline. So this saline water has to travel to the unsaturated system and reach the aquifer. No. So we need to handle with a large model, several thousand of square kilometers. The salinity is very high. We are talking about 150 grams per liter. This is a lot. So numerically means that you need to have a stable model, and to solve this, you need to require high level of discretization, so fine discretization. Here, FEFLOW can do the job because we can work with local refinements in software triangular mesh. Nowadays, we will even do it much better because we have access to combination of triangular and quadrilateral meshes. No, we have a dewatering and reinjections schemes of several hundreds well locations. Makes complicated, so we need to actually script something, use the open programming interface to reinject the water. And we have a lot of open pits, and the period of these pits is 10 years. No. So all the flow is very dynamic and depends on the local settings, hydrological settings, but also on the change of salinity. We need to increase the resolution of and accuracy of the model to keep the simulation times reasonable. No? So it could be sometimes some contradictional, no? Meaning that if you put more elements, so it will take more time to run the model, but sometimes it's also beneficial because you solve so easily the problem now, and the simulation could be also accelerated. This is a small cross-section of one transient calibration with mining conditions and with the mark, no, the simulated heads, no, and here we have concentration profiles, no. As I say, I cannot mention many details about this, no, but the whole message here is basically possible to do this large 3D flow and mass transport couple models with FEFLOW to simulate groundwater and salinity conditions in practicable calculation times. This is the most important, no? Because you can simulate with many other solutions, but times is always very important for our projects. Calibration and uncertainty analysis. Every single license of FEFLOW brings you the package of FEPES, so I probably don't have to talk about what is PES. PES is the parameter estimation software developed by John Doherty in Australia, and we make a link to PES. So this link to PES is specialized or tailored for FEFLOW models. So you have done your FEFLOW model, we can take this model, understand what type of problem class you have, and then read your observation data, and from this observation data we can try to solve the inverse problem. So we minimize objective function. Nicely, you can see those information in the panels. No? You can also get a scatter plot, and you can immediately see a feedback of the quality of the calibration. We can work with constant zone or pilot points in 2D, 3D structure on structure meshes. We can work parallelized locally in a server or even in the cloud. So we have done several projects in Australia, South America, and Europe with parallelization in the cloud using the FEPES infrastructure. DHI also has the software as a service, SaaS, so you can use these facilities to extend your calculation capabilities, no, and increase the number of runs for the calibration or for the uncertainty analysis. As a small example from New Zealand, this is the environmental Canterbury. Here we have two DHI models. So we have a MIG model. This MIG model was used to estimate accurately the groundwater recharge. So MIG is a catchment hydraulic model, and we have below our groundwater FEFLOW model. So typically, we will estimate recharge, pull the recharge in FEFLOW, run the model, and do our FEFLOW, our work concentrated on FEFLOW. What we have done here is we basically try to use PES to enhance the distribution of recharge coming from MIG. So we set a pilot point problem. So we have several pilot points, no? We have prior knowledge coming from MIG. So MIG used information on land uses, soil types, etc., to give us some patterns of recharge. This is what we have here on the top, no? But maybe this recharge was not is not 100% accurate in some locations, so we need to somehow calibrate this recharge, no? And what we do is we solve the inverse problem, so we create a pseudo layer with pilot points. These pilot points, they take the information coming from MIG, then calibrate a correction factor, no, which will multiply the distribution coming from the hydrogeological software, no, and then the result of these two layers of distribution will be used in FEFLOW for the calculation. Post-mining, rebound, and pit laying. So now we are moving to another type of process, which is also very important and complicated. So we need to simulate this. So we need to estimate, okay, what is the different water volumes in the system inside this open pit or cast, no? So we have some problems with water quality impacts, or is the stability of the slope still good enough, no? So how do we simulate this in FEFLOW? This is also a transient problem, no? So we have different procedures. So the most simple is the so-called pseudoporous media material in the pit. So we try to simulate an air layer inside. So how do you simulate air layer in FEFLOW? It's basically by increasing a high porosity one and playing with the high conductivity, no? That is a very simple approach and give us a quick estimation of the flow systems happening in the area of the pit lake. We developed already some time ago a plugin which tried to simulate this connection of lakes in FEFLOW, no, this so-called IFN lake. Now, these IFN lakes say automatically boundary conditions depending on the infiltration volume or on the retained volume in this location of the open pits. No? And third option, we have a coupling to surface water software, so we can solve very accurately what is this flooding distribution, these wet areas by using my 20-watt flexible mesh. Coming back to one of the approaches with the IFN lake. So by the way, this plugin is free available. So if you want to get a copy of this, please don't hesitate to send me an email. I will give you my contact details afterwards. And basically here you provide as usual all the weather information. What is the precipitation, evaporation? Do you have some surface inflow, outflow? No? And the plugin simply estimates what is the heads based on a volume relationship curve. No? And this head is set as a boundary condition in FEFLOW, fluid transfer VC, and will be dynamically updating depending on the volume inside your reservoir. Since about a year ago, we implement a more realistic approach by doing a fully hydrodynamical coupling between surface water and groundwater. So we take the full advantage of the software My21 for estimating processes of rainfall, surface runoff, infiltration of pond and water, etc., groundwater flooding events, river aquifer interaction, mine water groundwater interaction. So in principle, it works very simple. So you have your FEFLOW model, you have your My21 models for surface water modeling. No, FEFLOW will work with variable saturated or phreatic conditions. No, you can also include some heat transport and salinity transport, and the two meshes will be combined. So they don't need to be exactly the same. So My21, it has a flexible mesh, so it can have a triangular mesh combined with quadrilaterals, and FEFLOW, as always, has a triangular mesh. And the method is very simple. In FEFLOW, you define via discrete feature element and say what is the coupling area, what is the coupling region where you want to provide estimation of fluxes between these two softwares. No, that's it. Then the software My21 and FEFLOW do the entire job. So there is a time stepping control automatically in FEFLOW. In My21, fluxes are changed following a one order relationship. No, and last but not least, you have the very powerful visualization options of FEFLOW to represent the different information from the surface water modeling. So water depth, you can distribute, present the pressure, temperature, salinity. You can display the exchange fluxes, what is in between the interface, surface water, groundwater, etc. One example from here from Germany, is a lignite mine, so it's already closed long time ago. So we build a FEFLOW model here. We have a lake, the Cottbus Lake. No, the area of the catchment is about 174 square kilometers. We have few streams and some main rivers, so we have about 500,000 elements in the system. So still the model is relatively small, and this is a distribution of conductivity, and the green areas are different lakes that we have here. No? Lakes and streams. We did as usual a calibration of this now, and we try to estimate now what is happening with this lake. So the mine is not anymore operated, so it was intended to establish a recreational location, so it was partially flooded. No, and DHI provides a solution based on this plugin. So developed in that time the so-called IFN lake. where you can distribute or you can provide information of multiple lakes in the system and also set up boundary conditions automatically. So this is a very simple example, no? So what is happening here if your volume in the lake is being increasing, no, over time, so automatically the plugin will take the job of assigning boundary conditions. So you require the initial water level in the lake, no? Also, we can handle connected lakes, so you can have different lakes and different water levels, no? And depending on the head, so you provide behind digital elevation model, so DTM, and depending on this topography and weather information, the plugin is able to set the boundaries, no? And then FEFLOW will do the job to simulate the gradients in between the lakes, no? That is a small video. Let's see. So you can see here the different flux, the different gradients happening, no, from infiltration from one side through the pit lake inside the system, no. If this is not enough for you, we have extensive software documentation. So we have put always a lot of attention and importance on the different mathematical background of the software. So we have the so-called white papers, we have an online support and local help system. We have installation guidelines, demonstration exercise. There is a FEFLOW book that you can access via Sprinter editor. No? Each FEFLOW license comes always with a FEFLOW support. FEFLOW support is distributed. It is available for the different offices in DHI. So we have from local support in Australia, in Perth office. No, we have also some part of my team here in Berlin is taking care of the support in FEFLOW. We have a big community extending every year, and this community is very active through our MIC forum. And last but not least, we have a bunch of very interesting training courses, no? And I would like to draw your attention for a new training course that we are rolling out now. Is a special training course for mining applications. So we will plan to offer multiple modules, no? And we start with the module 1, which is related to opencast mining. So here you will learn all the different topics of how to simulate open pits in the context of mining applications, use FEFLOW to build the geometry of your pit or pit shell, how to set seepage boundary condition, estimate volumes over time, set up drainages, etc. And now we can do a simple live demonstration. So I try to set, because we really have 1 hour, and I try to set my threshold of 15 minutes to build a model. And let's see if I can manage this. So I will quickly explain you some details about the model. If you have specific questions, of course, you can always write me. I will be more than happy to assist you with your dedicated questions. So this is our super mesh view. So we have a pit here in the middle. It's a simplified geometry. And this example, by the way, I will talk in the training course with more detail. No? I would like to build a mesh with this. So I have proposed 6,000 elements. I use the mesh generator triangle, and then we have a mesh now coming in. Yeah, this is our mesh, so we always need to check the quality. FEFLOW has very nice options to identify the quality of the mesh, and this is very important to do because all the calculation result depends on this mesh. So I see we have, okay, this is in radians, interesting. We can always improve the mesh by doing some local smoothing. So you have multiple tools to select this border of polygons, or we can select the border, we can select the borders of the polygons and then switch the different nodes. And FEFLOW has some tools to do the smooth operation. This means we'll run on behind an algorithm to basically improve the position of these elements. No? Now we can start saving this file. And I have prepared already some data for the geometry, so we will build a pit here, no? And that you can see nicely, I will put this data in this container. It's called user data. So user data, you basically store any kind of information that you want. So I will put my different topography levels. I have a pre-mining, I have a pit stage number 1, and I have a pit stage number 4. I have prepared elevation data. I need to assign this elevation data to the model. And for this, I basically need 3 coordinates X, Y, Z, and then do a link to any of the parameters. Because this is point data, we need to fill the entire mesh. We will do basically a easy invert distance interpolation. You can see now, and interpolations take place in a matter of seconds, and I have my pre-mining level. I will do the same for the one of the pits, pit 4, 1 and 4. And here we have, and I will prepare also for the next one. Okay, the difference with the data is that now these points, this cloud of points basically is in the area of the pit, so then normally you have the contours, so then we can assign this data to the. So if we display the points, so we will see that the points are only in this area. And do the same for the next one. And now you have the information in the model as a surfaces, no? So what is the next step is you need to fill the information around this pit. So we have already some selections. Let's do the simple. Let's assume that only the elevation change inside this area. Outside is exactly the same what we have in the pre-mining. So I will copy this data and paste it and paste it again. And now I have the full elevation data in the model. So let's save this. And if you go to the 3D layer configurator, you can easily pass this data to the configurator, mining. Let's say the bottom is it's a constant elevation, and you can also define, fix these layers, add layers in between these, and very easily you start building your FEFLOW model in 3D using the elevation data that you have already prepared. I have the pre-mining level, the mining and the pit level 1. And now I take the next one, and okay. And you don't see this because it's internally, but as soon as you press OK, then FEFLOW will bring the mesh, the layer resolution, and tell you, okay, there is a conflict of layers, so we have to basically handle this. We can do the classical approach, set a minimum thickness, or we can do an extraction measure. So let's try the second one. I will accelerate the process by avoiding interpolation. We can just wait 1-2 seconds, and the mesh is generated. Yeah, so you have the mesh, save the model, and now if we look on this mesh, so the model is unstructured, so we have layers. See, the next layer is defined by the surfaces between the 2 pit shells, and the last one is just below. Right from the beginning, you see that the mesh is too coarse, so we need to improve it. So no problem, we have a mesh generator, TechGens, and this generator allows us to store this to remesh part of the model or entirely, no? And we can also define some surfaces. So this is the pit 1, and this is the next one is the. So let's see, this is the surface between these 2. Pit 2, and the next one is the. This is the what you will call the pit shell, no? And 3, and now we can take this 3, put it in the meshing panel, and I will take any of my secret numbers. So if you're interested, I will tell you the trick later, and take a volume for the elements, and I will remesh this, and FEFLOW will take the input volumes that we provide, layer 1, 2, and 3. We prescribe some surfaces, speed 1, 2, and 3, and maintain this geometry and remesh it inside, based using a maximum tetrahedral volume of 10 to the 7 cubic meters. No? This secret number comes from the distribution of elemental volumes. So there is auxiliary data. You should look basically before this and then get information. Now the mesh is ready. We can see we have a better distribution of elements. If I go to the layers, so I have element group 1, 2, and I have some surfaces where I will put the boundary of the piece. So let's save this model now. Save. The model has some boundary conditions now, and now let's imagine that we already have done the steady state run. So we are interested to set now our dewatering boundary. So we can just simply swap from faces to nodes, and here we have, if we zoom in, we have a set of nodes exactly following the shape of your pit. So we can go to FEFLOW and say we want to set a boundary condition, and this boundary condition is called seepage phase. No, and I have the seepage phase boundary condition, and I would also like to activate this boundary condition only in a specific time. So we create a time series, and we can put a gap. Gap basically means that you are going to deactivate the boundary condition in some specific time. So we have a concept called modulation function, which is a time series which multiply the value of your boundary condition. So if you go here to the model, say add parameter modulation function, you can take the modulation function that you want. You need a selection, and FEFLOW automatically will activate or deactivate the boundary in the specific time. Now you want to modify the elements, so you want to do the excavation, so you have a pit level of volume now. So you can say, I want to make this transient, this material in 365 days, and then I have another few times. So at the beginning, my entire mesh is active, and then I can say after a year time, this volume is gone, and then it keeps this deactivated until the end of the simulation. And like this, you can easily simulate all these different geometrical changes. Okay, because we are running out of time, let me show you some of the results. So I have put the two boundary conditions now in the model, and then simply run the simulation with some steady state conditions now. And this is the model. Let me show you the model. This is the model with the boundary conditions. So with the changes of the geometry. So we have a first level deactivated after 1 year. Then comes 2 years, I deactivate the next pitch and keep this until the end of the run. In parallel, I put the boundary conditions. This is a 3D model, so as we can see here, same model that we have. For the easier understanding, I just create a simple video that we can just play. No? We will see the changes. So the white line is the phreatic surfaces. We have the different hydraulic headlines in black color, and you can see the infiltration process at the end. So actually, I didn't start it from the beginning. This is the pre-mining condition. The water level is very high, and then I deactivate the first block. We can see already the local gradients happening in the mine. The area in red color is deactivated, and then it comes the next pit volumes, phreatic surface decrease. Again, water levels start decreasing over time. So if you, I will leave you my contact details. So if you're interested to know something more about the software, no, or specific detail of the presentation, so please do not hesitate and just send me an email, no, to cvi@dhigroup.com, and I will be glad to answer you these questions, no. So thank you again for your time. It was a pleasure for me to talk to you. Have a good day. Bye.